This is Mrs. Appia with Lesson 13, the graph of a linear equation in two variables. Student outcomes for this lesson. Students predict the shape of a graph of a linear equation by finding and plotting solutions on a coordinate plane. Students informally explain why the graph of a linear equation is not curved in terms of solutions to the given linear equation. Our essential question is, does the graph of every linear equation result in a line? In the last lesson, we saw that linear equation in two variables, ax plus by equals c, standard form, can be plotted on a coordinate plane, and each point, or ordered pair, xy, is a solution to the equation. Do you think it's possible to plot all of the solutions of a linear equation on a coordinate plane? Find the solutions for x plus y equals 6, and let's explore this idea. To find the solutions for x plus y equals 6, we can set the variable for x or y. Let's start by setting the values for x with positive numbers. Let's let x equal 1, 2, and 3. If x equals 1, 1 plus 5 equals 6, so the y value would be 5. If x is 2, y would be 4. If x is 3, y would be 3. Let's graph those ordered pairs. 1, 5. I'm going to pause the video and darken my graph lines so that it is easier to graph my ordered pairs. You may want to do the same thing. I've darkened my axes and I've graphed my first 3 points. At this point, are you convinced that the graph is a line? Let's put a few more points on here and discover that. Let's use some fractions. Let's use 1.5 and 2.5. If x is 1.5, then y will be 4.5 because they have a sum of 6. If x is 2.5, y will be 3.5. Let's graph those ordered pairs. 1.5, 4.5. 2.5, 3.5. It appears that our solutions are forming a line. What about numbers that might be in this quadrant or this quadrant? We could have a line, or rather a graph, that ends up looking something like this, or something like this, or something like this. So I'm not convinced yet that this is a line, although it appears to be so. So we've used whole numbers, we've used fractions. Let's try a few negative numbers. Let's use -1, -2, and -3 for x. And that would put our solutions into the second quadrant. If x equals -1, then y would equal 7. If x equals -2, y equals 8. If x equals -3, y equals 9. Plot those points. It appears that our solutions are still forming a line. What if the y values were negative? Let's let y equal -1, -2, and -3, and this time solve for x. Then graph those points. Based on all of the ordered pairs that we have found, I am convinced that the graph of this equation is a line. The question said, do you think it's possible to plot all of the solutions? I do not believe that it is possible to plot all of the solutions because we can keep finding numbers that are in between the given values. For example, in between 1 and 2, we could be graphing when x equals a half, or a fourth, or a third. So we can keep squeezing numbers in or having larger numbers. I believe there's an infinite number of solutions to this equation. Based on this graph, do you think the point 17/3, 1/3 belongs on this graph? Plot that point and determine your answer. I've converted 17/3 to an improper fraction, or rather to a mixed number, and I've graphed the point, and it does appear that it is on the line. So I think that it is. But is there a way that you could tell for sure? There is a way. What you would do is substitute it in this equation and see if those two numbers do in fact add up to 6. So we substitute 5 2/3 plus 1/3. 5 2/3 plus 1/3 equals 6. Since the left equals the right, we know that this is a solution to that equation. On your own, find at least 10 solutions to the linear equation 3x plus y equals -8. Plot the points on a coordinate plane. When you are choosing your variables, remember, if x has a coefficient, then x is a good variable to fix the numbers for, and then solve for y. Remember to choose some positive values, 0, some negative values, and some fractions. When you choose your fractions, you will want a denominator of 3. A denominator of 3, when you multiply 3 times that fraction, will give you a whole number, and that will give you a one-step solution to solve. Pause the video and come up with 10 solutions. Write the ordered pairs and plot the points on the coordinate plane. These are the numbers that I have chosen to use. Now keep in mind that your table may look differently depending on what numbers you chose. What I did is I substituted each of my values for x, and then I solved for y. These are the ordered pairs that I came up with. Then, let me show you the whole page. Then, graph those ordered pairs on the coordinate plane. This is what the solutions looked like for the values that I have chosen. What shape is the graph of the linear equation taking? It appears to be a line. Number 2. Find at least 10 solutions to the linear equation x minus 5y equals 11 and plot the points on a coordinate plane. When determining whether to fix your values for x or y, remember which one has the coefficient. We want to choose y values for this equation because y has a coefficient. This will result in one step to solve instead of 2 steps to solve. Remember to choose a few positive values, 0, and a few negative values, and a few fraction with denominator of 5. So I'm going to set my first y value at 3. Then I'm going to write my equation, x minus 5 times 3 equals 11. Then I'm going to solve for x. 5 times 3 is 15. Subtract, or rather add 15 to both sides of the equation, and the x value is 26. So my ordered pair is 26, 3. Pause the video and find 9 more solutions. Then graph your solutions. These are the y values that I chose. These are the x values that I ended up with. These are my ordered pairs. And here is the rest of the page. Keep in mind that your answers will be different from mine based on the y values you chose. Then I graphed all of my ordered pairs, and this is what my graph of the equation looks like. What shape is the graph of the linear equation taking? Again, it appears to be a line. Question 3. Compare the solutions you found in exercise 1 with a partner. Add their solutions to your graph. If we were doing that in class, we would do this activity. What we would notice, it says, is the prediction you made about the shape of the graph still true? If you added your classmates' ordered pair solutions to your graph, you would notice that they fall in line with your solutions. We're going to skip number 4 and go down to number 5. Joey predicts that the graph of negative x plus 2y equals 3 will look like the graph shown below. Do you agree? Explain why or why not. Well, let's take a look. We've got a point here, and here, and here, and here. Then we've also got this point here. These points appear to be in a line, while this one does not. So what I want to do is I want to check and see if this ordered pair actually is a solution to our equation. This ordered pair is 0, 0. So I'm going to write the equation, negative x plus 2y equals 3. And I'm going to check and see if 0, 0 is a solution. I'm going to substitute 0 for x. I'm going to substitute 0 for y. And check and see if it does in fact equal 3. The opposite of 0 is 0. 2 times 0 is 0. 0 plus 0 equals 0. 0 does not equal 3. So this is not a solution. If 0, 0 is not a solution, then this graph is not the graph for this equation. We could check other points, but once you know that one of the points is wrong, we know that it is not the graph of the equation. So I don't need to check any more points, even though I could. So let's make sure we've answered the question. Is this the graph of the equation? No. How do you know? 0, 0 is not a solution. Since 0, 0 is not a solution, the graph will not look like this one. Number 6 is a challenge question to do on your own. It says, we have looked at some equations that appear to be lines. Can you write an equation that has solutions that do not form a line? Try to come up with one and prove your assertion on the coordinate plane. To do this, you will write a linear equation in two variables that you think will not form a straight line. Prove your assertion by creating a table of xy values, solutions to your equation. Plot your points to show they don't fall in a line. See if you can come up with this, and we'll share our results tomorrow in class. Next, we'll go on to the lesson summary. In this lesson, you've learned The graphs of linear equations in two variables we've done so far appear to take the shape of a line. We can show whether or not a point is on a graph of an equation by checking to see if it is a solution to the equation.